Here we have a second type of turning point. As always, it's characterized by the gradient being equal to 0. So dy dx is equal to 0. This type of turning point is called a local minimum, although most people just refer to a minimum and give it the abbreviation min. As with all turning points, we identify their position by solving the equation dy dx is equal to 0, as we'll see when we come to doing some actual examples. We can identify the type of turning point by using either a sine table or by considering the second differential d2y dx squared. d2y dx squared is what we get when we differentiate dy dx. If we consider the sine table in this case, we saw a sine table in the last example, so we should know what one looks like. We take 3 values of x, and the middle one is always the x-coordinate of where the turning point actually happens. For example, it might happen at 4. We then take a point to the left of 4, for example 3, provided that there are no turning points between 3 and 4. If there are, we need to take a point closer to 4. We could take a point to the right, such as 5, with the same proviso that there's no turning points between 4 and 5. Since the turning point actually happens at 4, dy dx is 0 here. For this type of turning point, we have a negative gradient to the left and a positive gradient to the right. If we draw a picture of this, it goes down, across and up, and we can identify the minimum shape. If we now consider the second derivative, d2y dx squared, and this is the gradient function for dy dx, which follows since dy dx is the gradient function for y. So if we differentiate again to get d2y dx squared, we would expect this to be the gradient function for dy dx. If we consider what happens to dy dx, it's negative, goes through 0 and then becomes positive. So if we plotted dy dx, it would be sloping upwards, negative through 0 to positive. Therefore d2y dx squared, being its gradient function, would be positive. If d2y dx squared is positive, we can say that we have a local minimum.